Hi everyone. Um, in this video, we'll be dealing with the 86 and the 64 architectures. So mainly there are a bunch of architectures out there that you can explore on your own. But in this video, I will be focusing on the 86 specifically. So just to explain what is an architecture specifically. Imagine the architecture as the design or the way that the processor or the CPU is designed exactly. So, for example, in your computer, you have um, an Intel CPU. So, Intel CPUs are actually designed in a way that the 86 and the 64 architectures are the one that can explain exactly what the processor or the CPU is doing and why it's doing it um, this way and not another way. And it's a kind of description of how the processor is going to deal with the instruction of your programs. So this is just a brief idea about what is the purpose of an architecture exactly. So the points that we will be talking about today is the registers that I have talked about in the previous videos that and I have promised to explain them. We have also the memory and addressing modes. We have also the instruction set, specifically of the 86 architecture. We also have um, the calling convention, the calling conventions. What do we have also? I will be also talking about how to make a syscall, how to make syscalls. Yeah. So this is mainly what we will be doing in this video. So just try to focus with me and I think you will learn a lot. So yeah. So let's start with registers. So when we talk about registers, we have um, some kind of registers or a lot of registers that your CPU can use. But modern, I think, 86 processors have 832 832-bit like general purpose registers that we can just call them EIX, EBX, ACX, ADX, ACI, EDI, ESP, and BVP are a kind of special registers. But the one thing that you need to understand is that each register has a size of a 32-bit, and each register could be divided into sub-registers called, for example, for the EIX, that is the accumulator actually, could be divided into AX and AH and AL. And for example, AL could be the first 8 bit of the AIX, and the AH could be the 8 bits or the second 8 bits of the AIX. So AL abbreviation is used, for example, for the low part, and this is for the high part. And the AX is like the second part of the AIX. And the same methodology could be used for the EBX, the ECX, and the EDX. But the ECI and the EDI, let's say just another some special not that special, but some kind of special, yeah. Because the EDI and the ECI could be used together, for example, to chain some kind of instructions. For example, I remember just reading about the EDI and the ECI in the Practical Reverse Engineering book. You could check that out. I have already suggested that you read that book. Um, the EDI and the ECI could be used, for example, to calculate the length of a string just by chaining those two registers with the instruction repeat just to calculate, for example, the length of a string. And the ESP and the EBP are kind of too special because they are the ones used to track down a data structure called stack. that I will be trying to explain it later on. So yeah, so this is mainly what the CPU is going to use just to interact with the data. So now let's move on into the part where we need to talk about the memory and the addressing modes. So the first thing that I want you to know is how can we declare um, static data regions? This is the kind of question that we need to deal with. So to declare static data, we can use, for example, in assembly, the directive called data. So data is going to help us declare what we call static data regions. So for example, to declare, for example, a variable x, um, we can do, for example, db just to declare, for example, 1 byte of, for example, like that, 42, for example. And this instruction is going to declare a byte into the memory, actually, and initialize it with the 0x42, which is a 1 byte. Now, for example, let's suppose I want to now, instead of declaring 1 byte, I want to declare, for example, a word. We can declare a word with the same way, which is actually um, just using the dw instead of a db. So instead of declaring 1 byte, I want now to declare one word. And actually, um, one word is actually 2 bytes. Now let's suppose I want to declare another variable, which is z. For example, to declare z, we could just use a double word now instead of a one word. So for example, let's suppose and this is the 82 bytes. So this is like now we are going to declare a double word, which means it's going to be a 4 bytes. For example, 12, 32, and 43, 32. I will be doing some spaces to just identify the bytes in the data section. Yeah. So this is just a simple example of how you can declare static data. Now let's just move on to how can we declare arrays. So to declare arrays, you can, for example, do array. Let's just, for example, do an array of 3 bytes. So for example, to declare an array of 3 bytes, you could use db, and then you could, for example, just put the bytes that you want to declare. So it's pretty simple. So let's suppose now I want to declare an array of 12 of 12 elements, but I want to initialize each element with the 0x42. So dub is used to declare, or is used to initialize the elements in the array, and db, you already know it. And when you do, for example, db 0x12 dub with the 0x42, I'm sorry, it's not 12 elements, it's actually um, yeah, it's actually 12 bytes. Yeah. So with the 0x42 value as the one that will be initializing that, yeah. So this instruction is going to create an array with the size of 0x12, and is going to initialize each byte to 0x42. Yeah. So this is what it's going to do. So just to move on now more, for example, um, if I want to, I don't know, maybe just initialize a string, for example. So to initialize a string, we could use db hello world. So for example, db hello world, and then we forgot the zero just to terminate the string, to let your computer know that this is a string. And you obviously know that when you declare a string, it always ends with the byte 0. Yeah. So this is basically going to declare a string into your memory. Yeah. So this is basically how you do static declarations of any data regions that you want. So all what you need to do is use the directive data. So another interesting thing is how can we, for example, how can we know the size of the directive, for example, when trying to access those variables or those values specifically. So to do that, for example, there is an instruction called move that is used, for example, to move variables into to move variables or registers or values from one register into another register. And to do that, for example, you could, for example, do move 0x1 into AIX. This is basically just some basic instruction in assembly and specifically in the 86. So, for example, when you wanna move 1 into AIX, you can just do move AIX and 0x1. So it's pretty easy to do. So now, for example, let's suppose I wanna try to move that one specifically into the first byte into some memory region. Well, to do that, we can do, for example, move byte, for example, PDA, for example, into EBX, and I want one to be moved into the first byte of the EBX. So the EBX is going to be um, an address into the memory, and by using the two brackets, I'm going to access that address into the memory. So this is used for access and this is the address. So I want by this instruction to move the one into the first byte that is pointed to by the EBX. Let's suppose I want to, for example, move a word into the same location. So to do that, all what we need to do is just change a little the size of the directive by doing a word. So by doing that, I'm going to move one word, which is, for example, 2 bytes into that location in the EBX. That location pointed by the EBX, I'm sorry. So, for example, if I want to do a double word, it's pretty simple. All what we need to do is change the word with the double word. So basically what the move is doing, it's taking the first value in the right and it's assigning that value into the element that is in the left. So for example, if we just try to do the same thing just using registers, for example, if I do EBX, if I do move EIX EBX, it's going to move the value that is in the EBX, and then it will be putting that value into the EIX. This is just another example of how we can do this. We can also move constants if we want. For example, 0x2 3. We can also move into regions as we have seen. For example, I want to move 0x1, 2, 3, for example, into the memory region pointed to by EIX. It's another also alternative to do this. So this is mainly what we can do just by using the move instruction. So now just in the same subject about moving stuff and doing all of that, there is actually a data structure called stack. So stack, guys, is really interesting. So just to understand what the stack is doing, imagine you have, for example, let me just open up Sketch AO. Yeah, so what do we have? So for example, let's suppose we have um, this is basically um, what the what the data structure stack is doing. So for example, let's suppose you have a data structure called stack. So what the stack is doing, guys, is it's going to you have actually like a bucket where you have to put when you have to put, for example, elements on the top of that stack, and you can, for example, also get the elements from the top of the stack. So, for example, let's suppose you have a list of elements, let's say 2, 3, 4, and 5, and you want to put them in this data structure. So, To put the 2, all what you need to do is use the instruction push. So when you do push, for example, push 2, it's actually going to push the 2 into the stack. And eventually you will have the 2 um, on the top of your stack. For example, when you do push 3 also, it's going to push the 3 in the stack. And same goes for 4 and 5. Now, for example, if I want to get the 5, you need to use the instruction poop. And you need to specify the destination of the 5, for example. To do that, your CPU, for example, uses registers to do that. So you can use, for example, EIX. So for example, when you do poop EIX, you actually like it's actually like saying to the computer, okay, I want to poop EIX, means I want to get the element at the top of the stack into the EIX. So when you do that, you actually do EIX equals to 4. And then you actually do another magic behind, which are the resistors that I will be talking about, which are the EVP and the ESP. Yeah. Okay, so this is basically what the stack is doing. Another interesting just visualization you can just look at is, for example, I want to push, for example, 32. It's going to push 32. If I want to push 45, it's going to push 45. If I want to poop, it's going to poop them. It's going to poop 32. So this is basically what you can do with the stack. You have two kind of operations, which are the push and the pop. So this is mainly what you will be doing with them. So for example, so the kind of instructions that you can do is, for example, like that. We can also push registers in the 86. For example, let's say you want to push EBX, so you can push EBX to. Let's say, for example, now you want to pop into the value into the EX. So, for example, if we want to just try to make a little simulation, so I have pushed 0x123 and then I have pushed EBX, let's say into the EBX we have I don't know, for example 0x 1. So until this moment I have um, pushed um, for example 0x123 and 0x1 into the stack. For example, when I pop EIX, it's going to be the last element that was pushed into the stack. So AIX will be equal to 0x1. So yes, so this is mainly what this is gonna happen when you try to push and pop stuff from the stack. So another interesting instruction in the 86 is going to be the load effective address. So the load effective address, for example, like in this instruction, it's going to be loading the address of the memory that was pointed to by, for example, the second operand, which is the right side of the instruction. So for example, in this we are trying to access the memory region pointed to by EBX plus 0x1. So 0x1 is just the offset from the address that is saved into the EBX. So when we do load effective address, it's actually going to load that value into the AIX. So it's going to do like AIX, so will be assigned the address of that memory region, which is ABX plus 0x1. So this is mainly what the load effective address is doing. Just moving on now into some arithmetic and logic instructions, we can find the add. So for example, the add is a pretty famous one, which is we almost use it a lot. So it's going to be doing just some simple adding operations. So for example, when your CPU wants to add two numbers, let's say you have 2 and you have, for example, 1 and 2, and you want to add them, he's going actually um, to move the 1 into the register, and then he is going to move the 2 into another register, and then he is going to do the add for you. So add will be actually doing AIX equals to EIX plus EBX, and the result will be saved into the left operand, which are the EIX. So this is mainly what the add is doing. The same goes for sub actually. Sub is doing the same. You do, for example, sub EIX EBX, it's going to be EIX equals to EIX minus EBX. So always you do that minus the other one, and then you save the result into the first one, which is the EIX. For example, if we have switched them like that, it's going to change the behavior into EBX equals to EBX minus EIX. So this is basically what will be happening. Yeah, so if we move on more, we have also the increment that is going to increment. For example, if we do increment EIX, it's going to be incrementing the EIX by 1. We have also the decrement that is going to be, for example, decrementing the value that is saved into the EBX, decrementing that value by -1, that means by 1. We also, what do we have also? We have also the multiplication, which is the multiplication, which is going to multiplicate, um, the value that is, for example, in this example, into from the EIX into. I'm sorry, it's I said like it's with 2m, but it's with only 1m. Yeah. So the emul will be actually trying to multiplicate um, the value that is in the AIX with 2. Yeah, so it's pretty basic. We also have the IDIV, which is going to do the division for us. And another interesting thing is that, for example, when you want to do the division, the rest should be the rest is stored in the EDX. Yeah, so the rest should be stored in the EDX. So for example, when you do EIX divided by 2, you actually find the result of the division into the EIX, and then the rest will be eventually stored into the EDX. Yeah. So what else do we have? We have also the AND and the OR. So for example, if we do AND of EIX with 1, it's actually going to do the AND operations. We have also the OR, the XOR. What else do we have? We also have the NOT that is also useful. That is going to do the negation for us. If we want, for example, let's suppose AIX contains 1. If I do, for example, the NOT AIX, it's going to give us 0, and if it was 0, it's going to be 1. Means it's always the opposite if we do the NOT operation. What else do we have? We have also the shift left and the shift right. That is also really interesting since we have talked about in the requirements video. The shift left is going to multiply, for example, by the number of the shifts that will be passed into the parameters. And if you remember that we have talked about the shift left and we have said that is going to do a multiplication by 2, and the shift right is going to do the division by 2 of that number. So for example, when you do EIX 0x1, it's going to multiply EIX by 2, and if we do shift right, EIX 0x1 is going to be dividing the EIX, or the value that is in the EIX, by 2. So this is mainly what is happening when we talk about the arithmetic logic and all of that kind of stuff in the 86. Now, one interesting thing to talk more about is the control flow of the instructions. So in the 86 processors, we have the instruction pointer, which is the EIP. I cannot see it in here. Okay, um, there is actually a register, a special register, actually called the EIP that I have talked about, I think, that is going to be saving the current instruction or the next instruction that will be executed. So for example, let's say you have, for example, 0x1. Let's go back into the code. So let's say, for example, we have, so this is, let's say this is 0x, let's say this is 0x1. Let's suppose we have also 0x2. Um, let's say, for example, it's an OR with the ix0x2 that is going to do an OR. So basically, guys, the instruction pointer is really important because the instruction pointer is going to point to the next instruction that will be executed just to tell the processor or the CPU that he is going to execute that instruction next. So for example, in this uh, in this line, so the AIP is going to be 0x2, and in this line the AIP is going to be pointing to the next instruction too. Let's say for example we have this 0x3, which is the next instruction, which is like that. So the instruction pointer is really important, guys, and to implement the control flow, for example, in assembly or in any kind of program, when we talk, we need the instruction pointer because he is the one that will be jumping across the code that will be executing. So, for example, um, let's suppose I we have I don't know, for example, let's suppose, for example, I have these kind of instructions. Let's add more instructions. Let's say 0x4, not EIX. Okay, let's suppose this is actually in a block, for example, called, I don't know, just call it code. Okay, this is, for example, E code that would be executed. And let's suppose there is another code like this one. For example, this is another code. Okay, let's delete all of that. Let's suppose let's suppose this is the main function, and this is another function that has this code. Let's say, for example, I wanna just do move EIX0x1, move EBX0x2, and then add EIX EBX, and then I want, for example, to jump into that code. So all what you need to do is just do a simple just jump into that code. For example, you do jump code and then you jump to the code label. So this is called a label, and when you do jump into the code, it's going to be jumping into that code, and once it finishes executing those instructions, it's going to execute the rest of the instruction that it has. So yeah, so this is basically what is happening. Just one thing to mention is in this place we have to do that. We have to specify for him that this is going to be a code to be executed. Yeah. So this is basically what is happening for now, and the next like instruction that should be implemented to implement the control flow in any kind of assembly code is the compare. So for example, let's suppose um, I don't know, for example, let's suppose this is a block that will be used to print win. Let's call it win, for example. And let's suppose there is another block that will be used, for example, for fail. So if I want, for example, to implement now a function that is going to, for example, check if a variable x is equal to a number. So basically, let's say we want to implement this. So if I want, for example, to implement if AIX, for example, equals to something, it's going to be printing win, otherwise it's going to be printing a fail. So to implement this one, we can just use, for example, we will be trying to move, for example, a value into AIX. Let's suppose it's 0x1, and then let's suppose I'm going to compare the value that is in the AIX with the 0x42. So for example, compare what's in the AIX with the 0x 42, and then based on that I'm going to jump into a specific location. For example, this this GE means that we will be jumping to the win if it is equal. What does that mean? For example, the compare instruction is actually going to um, do the conversion of EIX with 0x42, and what's actually going to do, it's going to set flags, um, and it's going to do the the subtraction of or the subtraction, yeah, of the EIX. It's going to subtract from EIX 0x42, and then it's going to set the flags, and the specific flag that we want to know is actually the Z flags. So just to look at the flags in the 86 architecture, so flags in the 86 architecture, flags and assembly, yeah. What do we have in here? So yes, so this is mainly the flags that we have. So we have actually a lot of flags, but the flags that I'm really interested in are the zero flag, which the zero flag and the sign flag. So zero flag is actually, guys, gonna let us know if we have like an operation that ended with a zero, or means, for example, when we do EIX minus 0x42, it is going to subtract from the EX that value, and if, let's suppose it is actually 42. If it is 42, actually it will be setting, when we do the conversion of EIX with the 0x42, it's going uh, to set the zero flag to 1, which means that we have done an operation that gave us 0. So yeah, so this is basically what's gonna happen. So the zero flag gonna be set to 1. So the jump equal will be jumping to the win function if the zero flag um, is 1. So yeah, so if we do now jump equals to win, it's going to be jumping to the win. Otherwise, it's going to be jumping to the fail automatically. So yeah, so this is basically what's going to happen. Let's suppose that it's going to be printing the fail and it will be doing exit, just to make sure that we don't jump into the fail, and then we don't jump into the win and then we jump back again into the fail. So we will be printing, for example, a win message, and then we will be exiting, and then we will be printing, for example, in the fail, a fail message, and then we will be trying to exit too. So this is just um, a pretty basic control flow in any kind of assembly code that you will be dealing with. Now, just another interesting thing that we have just to talk about are actually how can we call functions and how can we return from functions. So basically, let's suppose we have a function. Let's call it fn, for example. Let's go, it's gonna be doing something and then it's gonna be returning. So this is the read instruction that is going to be returning from a function. So basically it's going to disallocate something. It's going to be disallocating some bytes that we'll be talking about, and then it's gonna be actually disallocating the struct frame of the function, and then it will be going back into and then it will be returning the flow back into the main function. So basically, to call this function, we can, for example, do this call. Let's just call fn, for example. So this is going call the function fn. So this is going to call the function fn. So this is a pretty basic one. Now, just now to understand more what is happening about functions, I need to dedicate some time just to explain to you something called stack frames. So basically, guys, stack frames are the way your computer is dealing with programs when they are trying to be, um, let's say, compiled and run into your computer. So there is a lot of magic happening by the compiler just to generate for you the assembly code that you will be seeing in the text section. And one of them is actually not just random, just it's just he's not just doing all of that by the randomness of stuff. He is actually based on some conventions. So I will be trying now to explain some of the calling convention that can be used to call functions. So to call functions, we can use something called the C declaration, which is a pretty basic one used by the 86. So the C declaration, or the CDECL specifically, you can search on that if you want, which is the CDECL, is a pretty famous one that is used by the 86 architecture to call functions. So mainly what it will be doing, guys, it is going to be calling a function in a way that is going to allocate a new stack frame for that function. So the question that arises in here, what does a stack frame means exactly? So let's explain it a little, guys. Imagine stack frames as a place into the memory. So this is your memory. Let's suppose so this is your memory. So this is your memory. Let's say this is your memory, and you have actually your memory could be divided into two regions. One region is for the static variables and the static local variables, and the other one is used for say for the dynamic variables, which is one called, I don't know if you know the name, but one is called the heap and the other one is called the stack that I have talked about earlier on. So the heap, guys, is used for anything that could be declared dynamically. So for example, when you do in C, for example, when you call m allocation, so malloc. So malloc is a pretty famous function that is used to allocate, for example, a memory block with with a fixed size. So malloc, guys, is going to allocate memory into the heap because the allocation is done dynamically. So the heap is actually used for anything that could be allocated dynamically, and the stack is used for anything that could be allocated statically. So for example, when you do in C, for example, when you do, for example, in C int x, let's suppose you have a main function. Let's suppose you have a main function that is having, for example, this, and is going to allocate x equals to 1 and then y equals to 2, and yeah, so this is basically just a simple main function. And don't forget the return 0. Let's suppose we have another file. That's better. Yeah, let's just call it learn.c. learn.c. Yeah, let's suppose you have this C code. uh, Include, okay, okay, okay. hmm Okay, let's suppose you have this one in front of you. And you have, for example, int x and int y, and for example, int z that is going to be doing a um, that is going to be allocating some dynamic memory for you. So I will be casting that into that, and then I will be doing malloc with the size of the int, which is the size of the integer. I'm going to be allocating, for example, I'm going to be allocating four values of that, four values of integers into the heap, and then I'm going to return the address of the first element into this z. So this is basically what is a something called dynamically allocated, um, dynamically allocated, and this is actually statically allocated. and this is also statically allocated. So this is gonna be going into the stack, and this is gonna be going into the stack, and this is gonna be going into the heap. So yeah, so this is basically what's going to be happening, guys. So just to look more into the details now, we will be trying to understand how exactly um, this function main is going to be called into the stack, just by forgetting that there exists a dynamically allocated value into the main. So for example, when we talk about specifically the stack, um, and the stack is actually going to be allocating um, for each for each function we will be allocating a stack frame for that. So let's suppose this is the memory. So for example, I will be taking a branch from the memory. So this is a place and this is a place, and I'm going to say that this is the stack frame, um, the stack frame of the main. Means that this region into the memory is going to be allocated for the main function. Let's suppose we have another function outside of the main, which is called, for example, sum. Sum is going to be taken int a and int b, two integers, and it's going to be returning the sum of these two elements. And then let's suppose it's going to be doing that just by adding them into another variable called b, and then it will be returning c. And then let's suppose we will be trying to call this function, just for example, let's suppose int y is equals to let's suppose this is equals to 1, and then let's suppose that the z is going to be sum of x and y. Well, let's suppose that the name's a and b, which is better. Okay, a and b, and this is the result. Yeah, and then let's suppose I want to printf um the result of that. So result is equals to percentage d. Let's say it's result. Yeah, so this is a basic program in C, and now we want to learn how this program is gonna be transformed into assembly. So specifically, we want to learn how the compiler and the architectures are combined together just to generate for us um, are going to be combined to generate for us the assembly code that will be loaded later on into the memory and executed by the CPU. So to learn that, so I have explained to you that each function is gonna be having its own stack frame. So for example, the main is gonna be having its own stack frame, and the sum is gonna be having its own stack frame. So I have tried to draw a little graph for you just to explain how the CDACL calling convention is working exactly, or the C declaration calling convention is working exactly on the 86. So just to look at that, so imagine this is the stack frame of the main function. So this is, for example, the stack frame of the main function. Let's suppose it's going to be having all these kind of values. Now, one thing that sets apart the CDECL calling convention from the other ones, that it's saying like to do the calling convention, you need the first thing that you need to do is push the two parameters of the function that you want to call. For example, in our case it's sum, into the stack, and then you need to say, for example, something called the base pointer. So this is actually, guys, the base pointer. So let me go back and explain a little what the base pointer and the stack pointer are exactly. So let's just look at, for example, the example that I have talked about later on. Yeah, so basically this is the stack, and let's suppose you have pushed a 1. So actually guys, the base pointer is the base of the stack. Let's suppose this is the EBP, and then when you push an element, so let's suppose you didn't push anything at first, so the stack pointer and the base pointer are at the same level. But when you did a push of a 1 into the stack, the ESP is going to grow just by trying. So the ESP is going to be pointing to the top of the stack, and the EBP is going to be pointing to the beginning of the stack. So in our case, it's going to be pointing to the ESP is going to be pointing to the top of the stack frame, and the EBP is going to be pointing to the base of the stack frame. So this is basically what is going to happen. So in the 32-bit architecture, or specifically in the 86, when you try to push something, for example, when you do push of 1, this instruction is going actually to do ESP equals to ESP minus 0x4. So it's like saying to the stack pointer to be going to be growing up and just trying to push the 1 into the stack. So just one more information about the stack. It's actually shrinking backward instead of forward. So what does that mean? For example, when we try to grow the stack or push something, it's gonna be doing a minus. And when we wanna, for example, poop something, so for example, when you poop 1, it's going to be doing, instead of a minus, it's going to be doing the addition. So it's going to be adding 4 instead of doing a subtraction of 4 when trying to do a push. So to push a 1, do you need to subtract 4 from the ESP, and if you want to put 1, you need to do an addition of 4 to the ESP. So this is mainly, the 4 is mainly coming from the 32-bit fact. For example, when we will be talking later on with on the 64-bit on the 64-bit architecture is gonna be turning into an 8. So yeah, so this is mainly what is happening when we talk about the stack and the stack pointer. So just as a little conclusion, the stack pointer is used to point to the top of the stack, and the base pointer is used to point to the base of the stack. So in our case in here, when we want to learn about the CD-ECL calling convention, and we want to know how exactly this code is gonna be turned on to an assembly code. So basically this is what will be happening. So each each base pointer and stack pointer will be pointing to the stack frame of the current frame, and then once we call, for example, another function, for example such as the SAM in this example, it's going to be allocating a new stack frame for the sum function, and once the sum function finishes its work, it's gonna be returning to the main stack frame, which is this one. So just to understand how the CDECL now calling convention is working, so the first thing the first thing to do when talking about the CD CL calling convention is to understand um, is calling convention is to learn. For example, the first thing to learn is um, we need to pass the parameters actually in reverse order, and then um, we need we need to save the return address um, in the stack, which is typically, guys, the EIP, which is typically the EIP because it points to the next instruction. In our case, for example, when we call the sum, it's going to be pushing the address of this instruction. Let's suppose, for example, it's going to be, I don't know, for example, um, let's suppose this is the instruction, I don't know, 32, for example. So the AIP is going to be 0x32. So mainly when you try to call this instruction, it's gonna be like saying this is the instruction pointer that is gonna be next. So for example, this is at this point, this is the instruction of the printf, and when we try to call the sum function, it's going to push the instruction pointer, which will be pointing to the next instruction into the stack. So what else next do we have? So next thing is to push the old base pointer of the main stack of the main function or of the main or of the stack frame of the main function. What else do we have? Now we allocate space for the local variables of the sum function. For example, in our case, it is the c. In our case, it is for the c variable. What else do we have? Then we execute actually then we can execute the function. Then we can execute the function body of the sum. Then after that, we need to restore the stack frame of the main function. So um, just before that, we need to return, for example, in the 86, in the 86 assembly, the return the return value is stored in the AIX register. What does that mean? Let's suppose, for example, you have done for example, the addition of the A plus B. Let's suppose you have moved the A into a register, let's say, for example, EBX, and let's suppose you have moved the B into ECX. Now, what's next is that once you have done the addition of these two numbers, or these two registers, you need to return the value of the operation into the EIX. So basically, what this is going to be doing, it's going to be returning the value of the c into the AIX. So the return value of any kind of function is always into the AIX when talking about the 86. So yes, once you have done that, you have to restore the stack frame of the main function. So to do that, you have um, you have um, to restore the old base pointer of the main function and you have also and then you have to restore the instruction pointer, the AIP register that you have saved in the stack. Now let's now move on. So this is basically the kind of instructions that you have to do when just talking about the CDECL calling convention. And this is basically all what you have to learn. Now, just by looking now at the image and the code at the same time, by try to visualize stuff that I have tried to draw in here and the code. So this is basically, let's suppose now we are at this line. So let's suppose we have now executed int a equals to 1 and int b equals to 2, and now we are at the point of just trying to affect, for example, assign into the result the sum of a plus b. Now what the let's say the compiler is going to generate for you, or what the computer is going to do specifically, it's going to be trying to do some kind of assembly code. Now I will be trying now at the same time try to convert this code into assembly and then try to visualize at the end of the video what is happening exactly, just to link or chain everything just for you. So okay, let's try to redo the same stuff now, but instead of doing that in C, let's try to convert this code just using our hands into assembly. So to convert that into assembly, so learn to, well, just call it learn to dot assembly. Okay, just to try to do that, or try to convert this code, um, I will be skipping some parts, and then I will be trying to suppose that this is the main um, code. So this is the main code. Okay, it's going to do stuff to do some stuff, and then it's going to be calling the function which is sum. Let's suppose it's going to be calling sum. So this is the implementation of the sum now. This is what the sum will be containing. So the sum actually will be doing um, as we have talked about. So the first thing to do is um, before just calling the sum is to push the A and the B into the stack. So to push the A and the B into the stack, before we do even the calling of the sum, we need to push them into the stack. So we have talked about just the fact that we need to push or to pass the parameters actually in the reverse order. So to do that, we have to push the B and then we have to push the A. So to do that, we can just do push, for example. Let's suppose we have before that move EIX 0x1 and move EBX 0x2. And then we will be pushing EIX and then we will be pushing EBX. What this will do is actually we need to push in the reverse order, so we need to push the EBX first, and then we need to push um, the EIX. So this is the reverse order of them. So once we do that, we need now to call the sum. So now we have the parameters are pushed, which if you can look at the picture, so this is the stack frame of the main function. Now I'm trying to call the function sum. So the first thing that I have done is pushing the argument 0 and the argument 1. So the argument 0 in the reverse order. So I'm going to be pushing the B and then I'm going to be pushing the A. So this is basically what I have done. So just by looking just as a first insight on the stack frame as the main function, I have here just noted that the EBP was in, for example, at the address 0x28 and the ESP was at the address 0x20. So this is gonna be the one that is going to be tracking down the ESP and the EBP. So by doing the push of the B, the ESP is going to be growing just by subtracting 0x4 from it. And then once I push the A2, it's going to be doing another subtraction of E4 from the ESP. So the ESP at this position is going to be 0x minus 4 minus 4, which is 0x 12. So once we have done that, so it's going to be subtracting 8 from the 20. So at this position, once we have pushed the A, it's the ESP is going to be 0x12. So this is what these two functions have done. So at this point, the ESP is going to be 0x12. So this is basically what the ESP is going to be. And the EBP is going to be 0x, the same value as before, which is of the stack frame of the main function, which is 0x28. And now, once we have called the sum, it's gonna be doing like it's gonna be pushing the AIP, I'm sorry, and then it is going to be doing ESP equals to ESP minus 0x4 again, and then the EBP will look the same also. Um, 0x28, and this is gonna be 0x C. Is it a C? Let me see. Yes, I suppose it's gonna be a C. Yes, it's gonna be a C. So what else do we have? Let me just know if that is C or not. I just forgot if it's a C or not. So okay, it's gonna be 0x12 minus 0x4, and then you do the hex. No, it's not a C. The hex of 14. Yeah, it's any. Yeah. So this is mainly what will be happening when we will try to call the sum. So we will be pushing the AIP. So the ESP is going to be the instruction of the print. So if you look back in here, so this is the instruction. So the IP will be looking will be pointing, I'm sorry, to the next instruction, which is the printf of the result of our result. So it's actually going to be that instruction. So we need to push that. We need to save it. So once you want to save any kind of registers, the way you do that in the 86 is just by pushing that register or that value into the stack. So yeah. So once you have done that, now we are now into once we do the push EIP, it's gonna be doing all of that, and then another instruction is gonna be to jump into the sum, which is the sum function. Yeah. So once we are jumping into the sum function, we want to write a function that can build for us uh, the new the new stack frame. So the first thing to do is whenever we are in another function, we need to create a new base pointer specific to that stack frame that we are in. So to do that, we need first again to save the old base pointer. How can we do that? So we push it. We push the base pointer into the stack, and the ESP is going to be shrinking too. It's going to be growing, I'm sorry. So it's gonna be 0x8. Um, is it an A? I don't remember. Is it an A? Yes, an A. Okay, the EBP is going to be uh, now the same until this moment. It's gonna be the same. It does not change yet. And then I'm going to change the new EBP, which is this one, the new EBP with the new stack pointer that is pointing to that just after the push. So I will be moving into the EBP, the ESP, just to just to say to the computer or to the to the computer specifically that I'm going to take the old base pointer and I will be trying to make a little transition of the EBP from being in this stack frame to this stack frame. So this is how exactly we allocate a new stack frame into the computer. So yeah, just by taking the base pointer and the stack pointer at the same level, now we can create or we can allocate new variables now for the stack frame. So what do we have now? We have, for example, in this code, we have c equals to a plus b. Now the question that arises, how much um, space do we need to allocate for the int c specifically, since it's a local variable? So as you can see, the stack is mainly used, for example, when you do any kind of static declarations of any kind of variables that is static, it's actually allocated in the stack. The same goes actually for the main. The A and the B will be in the stack frame of the main, allocated as int A and B, and they will be allocated in the stack. The same goes in here. When we are in a new stack frame, for example, in this case for the sum, it's going to be allocating for the C also the space needed for it. So just to know how much data we need to allocate, we need to know the size of the integer on the C. So for example, to know the size of that, we can use, for example, the function size of. We can, for example, printf this let's say percentage long integer, for example, of size of int, for example. This is gonna give us the size of the integers. So the size of the integer is 4 bytes because the size of is returning the size of the type passed to it, just using the bytes as a number. Okay, so now we have the number of bytes that the C could be having. So the C needs 4 bytes in memory to be allocated. So to allocate a C, we need to subtract. So basically, this is how allocation of static variables is happening underneath your computer. So this is basically how your compiler is generating code. So for example, when I'm trying to mimic actually what the compiler is doing, and at the same time the compiler is basing his own methodology of generating assembly code for you on convention. So don't forget that all what I'm doing is based on the CDECL convention. If we change the convention, the assembly code may change. So this is basically what we will be doing. So for allocation of local variables into the stack, we subtract from the ESP um, the amount of space needed to to allocate such a variable. So now the ESP will be now ESP minus um, 0x4, which is 0x06. Yeah. So this is like saying to the computer, okay, I will be allocating a local variable, and this is what the ESP now is going to do. So don't forget that whenever you have, for example, so whenever you will be seeing the subtract or for example sub ESP, the amount of space you need to be allocating is always going to be using the sub ESP and the amount of space that you will be allocating in that stack frame specifically. So yeah, so we call this the function prologue, and you can just search for that if you want. It's a pretty famous one, function prologue. Okay, so this is the function prologue. So in assembly language programming, the function prologue is a few lines of code at the beginning of a function which prepare the stack and registers for use within the function. So yeah, so as you can see, so this is the function prologue, and it's basically used just for the initialization, let's say, of the stack frame. Now, once we are in the stack frame, the question that arises is how can we get the values of the A and the B that we have inside inside of our stack, since we have pushed them before we call since we have pushed them before we call the function, as we can see here. So to get these two values, we can use, for example, the offset of them from the stack. So for example, we can use the EBP as the one that will be identifying these two variables for us, or these two parameters specifically. So to get them, we can use, for example, the first thing we need to do actually is we need to move these two values into registers and then do the add operation, and then return actually the result into the AIX, as we have talked about when trying to learn about the CDECL convention. So to do that, we need first to move the two values of A and B into registers. Let's try to do, for example, ECX, or let's suppose I will be using AIX. It's actually going to be using ABP, since the offset, for example, of the A is EBP plus 0x8. As you can see, when we try to push, we have done a minus, and when we go, for example, in the lower stack, we need to use the plus. So the opposite of minus is always going to be the add. So, for example, this is the EBP, and we need to so for example, in this yeah, so this is the EBP, and we need to, for example, get the value of the A. We need to jump to we need to jump on two values, which are the AIP and the saved EBP. So because of the EBP that is in here, we need to jump on the EBP and on the saved AIP, and then we could get the A. So we have jumped 8 bytes of memory to get the EBP, or to get, I'm sorry, the A, which is the parameter passed as the first argument, which is this one. And for example, to get the B, we need to jump 4, 4, 4. We need to jump 4 by 3, which is 12 bytes, which is 0xc. So to get, for example, the B, we need to jump to the offset of EBB plus 0xc. I think it's pretty easy to understand. You don't have to be a genius to understand such a thing. So it's pretty simple. Now, once we have the offset of both of them, all we need to do is just give the offset of them and move them into the AIX, and let's suppose I will be moving the other one into EBX, EBP plus 0xc, and then I will be adding AIX with EBX, and then it will be going to do AIX plus EBX. Since now we have the value into the AIX, which is the return, now all what we need to do is to disallocate the local variable that we have allocated. We can do that just by doing add into the ESP. So let's suppose, guys, um, this is the function prolog. So this is the function main body, and this is the function and epilogue. Yeah, so to do that, we need first to add, for example, into the ESP0x4. Once we have done that, we have now, by doing add to the ESP0x4, we have done the opposite of this operation. So this operation is allocating, and so this operation is deallocating, deallocating, disallocating, um, the variable c from the stack. Now once we have done that, the next thing to do is to get the base pointer or the old base pointer back. To do that, we can do pop into the EBP, into the current EBP, um, pop into the current EBP the old base pointer. So by doing that, we are getting back the old base pointer. Once we have done that, we can do a return. There will be actually, we need actually to do a return, and there is a parameter that this instruction can take, which is actually um, how much data we are going to disallocate when trying to return to the instruction pointer. Another way of doing this, okay, let's suppose we want to return. So return at this position is going to pop into the AIP the current instruction pointer that will be or the current or the next instruction that will be executed, and then it's gonna be jumping into the AIP. So it's gonna be jumping into the printf once the sum function have completed its own functionality. So yeah, so there is a problem. We still have this A and B into the memory. We need to disallocate them too. We need eventually to do the deallocation of them too. So to do that, we can, for example, do add ESP. For example, since we have pushed two values, we can do 0x8 for each one of the variables that we have pushed. Or we can actually do, instead of doing that in the main function, we can do it in here. So for example, we do 0x8, and by doing that, it's going to be returning to the main function, and before it returns, it will be shrinking the ESP by 8. It means it will be deallocating the parameters passed to the sum before calling it. So this is, guys, basically the whole stuff behind behind the CDECL calling convention. You can search more about other calling conventions if you want on the internet, and a lot of them is actually really interesting. For example, another interesting calling convention you could look at, for example, is the fast call convention, which is used by the Microsoft. Actually, guys, the this is this convention is, for example, let's take a look in this. For example, he is in here trying to do a caller that returns the callee of 123 plus 5, for example. So the as you can see, like this is the CDECL, so it will be pushing the 3, 2, and 1 in the reverse order, as you can see, and then it's gonna be calling the callee, and then he's going to be removing all arguments from the frame. It's all about what I have talked about, actually. So a lot of what I have already said is written in here. So let's move on, for example, into this one, which is the Microsoft fast call or the standard call, let's say. So the Microsoft fast call is gonna be using the same perspective. So we have a function, so we have a main, and we have another function that we will be calling. So to do that, this is actually the function prolog. It's the same, and then is it's actually going to do another thing. So this is the main stack. So this is the stack frame of the main. So this is makes us actually like setting up the stack frame of the main itself. So it's pushing the EBP, then moving the EBP, moving the ESP with the EBP at the same level, and then it's pushing 3, which is the third argument. Actually, since it has 3 arguments, it has 1, 2, and 3. Now the interesting thing about fast call conventions that it's gonna be passing the first argument using a register, and the second argument using a register, and then the third argument it will be passed on the stack. So it's pushing the 3 on the stack, and then it's moving the 2 into the EDX, and then it's moving the 1 into the ECX, and then it's calling the print nums. Now if we take a look at the print nums, how this function is going to fetch the numbers that were passed to it using the registers and the stack. At the same time, we can see that this is the function prolog. Um, this is gonna be allocating 8 bytes, and then it's getting from the ECX, which is the one. So it is like saying, okay, I will be allocating two variables on the stack. Okay, one for the one and the other one will be for the two. So if we look in here, so move EBP minus 0x4 is gonna be the offset of the first variable on the stack, and I'm sorry, this will be for what exactly? Let me see. Since it's in, yeah, since it's the ECX, so the EBP minus 0x4 is gonna be for the first argument or the first variable in the stack, and the EDX will be for the second argument, which is the 2, and then we will be trying to call another function, which is the printf. Since it's a function, also the printf, we need to pass to it the arguments to uh, to call it. So to call the printf, we have pushed the argument 3. Since it's already on the stack, all what we have to do is just give the offset on the stack, which is EBB plus 0x8, since we have already pushed it in here. So it's pretty obvious why we have the plus instead of the minus, and since it's will be also having the argument 2 and the argument 1, then we also need to push them into into the stack. So this is pushing the argument 2, so this is pushing the argument 1, and then he is pushing the address of the string, which is the numbers you have sent, are %d, 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 and then he is calling the printf. So whenever you have a calling of any kind of functions in the 86, all what you have to do is just pass the parameters on the stack, or if you are dealing with for example, the fast call convention, you can pass them using the registers, for example, in here. For example, in the 86, you could use more than two registers to do that. For example, you can use ECX, EDX. I don't remember the other ones, but there are a lot of calling conventions you can use, but the main goal of this video is for you to understand what a stack frame is, how you can deal with that, and if you have managed, I'm sorry, to understand all of this, then you will be dealing or you will be doing good with the reverse engineering when trying to reverse binaries, because when you will be looking at the code that was generated by the compiler, you will understand that this is a function, this is used for the function prolog, this is used for the function epilog, and some theory sometimes can help you understand all of that. So yes, so now what's next is that I want you to understand also how we can make syscalls in assembly, and specifically on the 86. So in this example, I have tried to write an example for you on how to do a syscall, for example, or how to write, for example, a program in assembly and try to assemble it and try to execute it on your own computer. So to do this, for example, you can just go, for example, into your terminal and try, for example, NASM, which is the assembler that we will be using, which is used for by Linux. We can use it, for example, Linux. So NASM is a great one to assemble assembly code. So we need to assemble it. So to assemble it, we need to specify the format of the code that was written. So in our case, it's actually gonna be for an ELF, which is an executable linkable file. So we need to specify the name of the file, which is the example. I have called it example.assembly. So until this moment, we have get the .o, which is an object, if you remember the process of compilation in the previous video that I have talked about. So this is the .object. Now we have to link it using a linker. I will be using the linker of the Linux, which is the GNU linker, which is the LD. So to link it, I will be using the LD. I need to specify the format again. So it's gonna be ELF i386, and then we need to give it the object, and then I'll call the binary, for example, dash o example. Yeah. So if we look, for example, using example, we see that it's an ELF32-bit LCB executable, version 1 statically linked and not stripped. I didn't mention too much flags for the LD. For example, we can add the strip if we want. We can add, for example, this strip. Example, if we look down in the example, it's gonna be stripped, as you can see. You can just play around the flags as you like. For example, you can just check the manual of the LD and play with them if you want. So yeah, so if we run, for example, now our binary, we could get subscribe and follow at Ironbot in Twitter. So yeah, so this is basically, as you can see, how we can write assembly code and run it. Now, what's interesting is now we need to understand what this code is doing. So the dot data section I have already talked about in the old video. The dot text section I have talked about in the old video too. If you haven't watched the video, you can check it out. Now, what's interesting is that this is the main function, and I'm trying to do just a simple print function of this message. So to do that, I didn't actually use the function print. I actually tried to invent my own. So yeah, so to do that, I have actually done something called a syscall, if you have remember. So syscalls are used to translate or to switch from user mode to kernel mode, and that can let your program just, instead of doing some usual stuff, you will let the kernel do the rest of us. So it's like, okay, hey kernel, can you please write this message for me on the screen? On just to do that, I need a mechanism to talk with the kernel. So this is where syscalls came into the game. So yeah, so just by trying to move, for example, EAX, I have tried to fill some specific values into these four registers, and then by firing up a syscall, just using the interrupt instruction, I have done this. So why and how these numbers should be filled, you should um, this is where you should check out the Linux syscall table. So if we look at the Linux syscall table, so this is all the syscalls that you wanna have or that you want to, for example, call. So for example in our situation we have called the write, exactly, since we are writing something into the screen. So to write something we need to use the syscall name, right? So what is exactly the number of this syscall? So it's gonna be 0x4. So for example, if you want to do a write syscall, you need to put into the EIX 0x4. So this is what I have done. I have moved into the EIX 4. And next, what is the next argument? So the argument 0 is gonna be passed on to the EBX, which will be containing an unsigned end file descriptor. So the file descriptor, guys, is a kind of way to say to him where am I going to write the message that I want to write. So in this example, I have said to him that I want to write to the file descriptor 1, which is typically used for the standard output. So it's usually used for the standard output. For example, if I have write, for example, 2, it's gonna be the standard error. You can just uh, you can just check them out on the internet if you want. So the file descriptor is a way to say to the computer, okay, instead of saying I want to write to the standard output, I can just assign or map a number to the standard output, which is a 1 in our case. And the next argument is going to be the buffer or a pointer to a buffer. So the buffer is actually, guys, the message that we will be trying to print. In our case, it's the hello. So I have tried already to allocate some static data into memory by doing hello db and allocating a string, just terminating it with a 0, and then all what I have to do is pass into the ECX, as you can see, the address of the hello, or the address of the buffer specifically that I want to print into the screen. Now, the next parameter is actually the EDX. So the EDX, guys, is used for the size, is used for the count, and it's actually used for characters do you wanna, um, how much characters do you wanna print into the screen, taking in consideration that you have the buffer. So, for example, if I do in this example, I have set 43, uh, which is actually the length of the string, which is subscribe and follow me, Ironbite, and Twitter. I can switch that, for example, into let's say 16, let's say 15. Let's try what will be happening, okay? And before we see what will be happening, then I have tried to do to let's say launch the syscall by using the interrupt instruction. So the interrupt instruction, if you remember, is actually having an interrupt vector table that will be used, and when by specifying the 0x80, I'm specifying this whole table that you will be seeing in here. It means that it will be trying to check this table, and based on the 0x80, it's going to be calling one of those syscalls that are in here. Yeah. So for example, in this place, we have also another syscall that will be exiting the program. It's moving EIX1 and exoring EBX with EBX, means like it's saying EBX equals to 1. Just by exoring a register by its own, it's actually like saying, okay, EBX equals to 0. Yeah. So it's a pretty obvious one. Instead of just using move EBX 0, that's actually called an optimization used by the compilers mostly. It's just an optimization because the move EBX is much more is much more slower than just ignoring the EBX with its own. Yeah. What else? So if we look, for example, at the exit, so this is the EIX01, and the parameter that is passed by the EBX is the error code. So it's just like saying, okay, exit 0. So this is just equivalent. So this is equivalent. This is um, equivalent to exit 0 in C, if you know it. This is how you do exit 0, just using assembly. So what else do we have? So yeah, I tried to change the count and try to see what will be happening if we do it. So we do like the same instructions. So this is an ASM. We do the assembly and then we generate and then we execute again. So what else do we have? Oh yeah, it's because the file is in the desktop. I need to move it back. Yeah, okay. What else do we have? Let's see. I wanna nano example dot assembly. Say I wanna set, for example, 14. Then just run the code again. Um, okay. Let's try to run it again. And as you can see, we are now, instead of printing 43 of characters from the buffer, we are now printing just 15 of them. Yeah, so this is a pretty basic thing on how you can launch syscalls on your computer, on how you can launch syscalls specifically from the assembly code. So now, just as a conclusion, what we have learned in this video. In this video, we have learned how the compiler is generating the code, what are the stuff that is used to generate this code, and a bunch of some theory behind why is he's doing this and not the other way, and some kind of stuff. um what else do we have um to say at the end? Oh yeah, before I forgot, there is also something For example, the all the stuff that I have talked about is on the 86, but if we want to switch back to the 64, the register size will be much more bigger. So for example, in the 86, 64, so actually the registers are now just having some R at the beginning of their names. So instead of EIX, we'll have AirIX, AirBX, AirCX, AirDX, etc. etc. It means that the size of the register will be 64 instead of 32. What else do we have? The calling convention used. Um, the calling convention used, for example, in the 8664, you can just check them out if you want. There is a lot of bench of papers just to do that, but just to do a resume for you, when you do the 8664 calling convention, he will be passing the first four parameters into registers, and then the rest will be pushed into the stack, and the same goes on as the 86. I'm sorry. So yeah, so I think we have hit the end of the video. If you have any kind of question, you can just ask me in comments, and if you have any kind of other questions that you want to ask, also you can message me on Twitter if you want. Don't forget to follow me on Twitter, and goodbye.